In recent years, the rise of state space models has revolutionized how we think about sequence modeling in deep learning, especially in computer vision. Among them, Mamba stands out as a powerful alternative to transformers, offering linear computational complexity and the ability to process long sequences efficiently. But while Mamba excels at handling long contexts, most existing pretraining strategies still treat it like a short sequence model. This mismatch limits its full potential. Today, we dive into a groundbreaking new method called Separator for AutoRegressive pretraining that fundamentally changes how we train Vision Mamba models. The core idea: turn multiple unrelated images into a single, ultra-long sequence and let the model learn from the relationships across them, not just within each image. Let's unpack this step by step. Why Vision Mamba needs long sequences. Mamba's strength lies in its selective scan mechanism, which allows it to process sequences of thousands of tokens with near-linear efficiency. Unlike transformers, whose attention complexity grows quadratically with sequence length, Mamba scales gracefully. This makes it ideal for tasks involving long-range dependencies, like understanding complex scenes, tracking motion, or modeling spatial relationships over large areas. Yet current autoregressive pretraining methods for Vision Mamba are stuck in a box. They model one image at a time, treating each as a short, isolated sequence. Even when models like ARM, autoregressive pretraining with Mamba, use patches and clusters, they still process only a single image per forward pass. This is a missed opportunity because Mamba wants long sequences. It's built for them. So here's the problem: the model's capability doesn't match the task design. The solution, introducing the separator. To bridge this gap, the authors of introduce a simple but profound innovation: a dedicated separator, a special cluster of tokens inserted at the beginning of every image. Imagine each image divided into non-overlapping patches, then grouped into larger clusters. Now, before each cluster sequence, we insert a separator cluster, a block of tokens where only the diagonal positions are filled with ones, and the rest are zeros. This creates a distinct, image-agnostic marker that clearly signals the start of a new image. Now, instead of feeding one image at a time, we concatenate multiple images into one long sequence: separator, image 1, separator, image 2, separator, image 3, and so on. This transforms the pretraining task from a single image reconstruction problem into a multi-image autoregressive prediction task. How works: architecture and training. The architecture is elegant in its simplicity. During pretraining: 1. Images are split into patches right arrow grouped into clusters. 2. A separator cluster is prepended to each image. 3. All images are concatenated in row major order to form a single long sequence. 4. This long sequence is fed into a causal encoder, a unidirectional Mamba MLP block with only one scan, preserving the autoregressive nature. 5. The model predicts the next cluster at each step, including the next image's separator after finishing the current one. Here's the key insight: the prediction target for the last cluster of image 1 is the separator of image 2. This forces the model to learn not just intra-image structure, but also cross-image dependencies. The decoder uses causal attention, but with a twist. Within each cluster, attention is bidirectional, allowing the model to fully integrate local spatial information. But between clusters, it remains unidirectional, preserving the causal flow. This hybrid design ensures that clusters are treated as atomic units of prediction, while still enabling long-range context. Why this matters: beyond single-image modeling. Traditional autoregressive methods, like IGPT, AIM, or ARM, all operate on a single image. They serialize pixels or patches, predict the next element, and stop. But they're limited by the number of tokens per image. Breaks this ceiling. By stitching together multiple images into one sequence, the input length can be quadrupled or more, without changing image resolution or patch size. For example, if each image contributes 144 patch clusters and 16 separator clusters, a sequence of 8 images becomes 1,280 tokens long. That's 8 times longer than ARM's typical setup, and Mamba handles it with ease. But the benefits go beyond length. Because the model sees multiple images in sequence, it learns to distinguish patterns across different domains, improving generalization. It also becomes more robust to noise and variation, since it's exposed to diverse visual content in a continuous flow. The role of the separator: not just a marker. The separator isn't just a placeholder, it's a critical architectural component. The authors explore 4 types. 0 vectors, all zeros. All ones. Embedding-based, initialized with learned embeddings. Identity pattern: ones on the diagonal, zeros elsewhere. They find that the identity separator, with ones on the diagonal, performs best, especially after longer training. But surprisingly, the simple zeros separator also works well, with only a small drop in performance. Why? Because the separator must be distinct from image content, but not so strong that it interferes with learning. The zero separator is clean, unobtrusive, and computationally cheap, making it ideal as a default. They also test separator position, before clusters SC, after CS, or alternating SCS-CSC. The SC configuration, separator before clusters, wins in both accuracy and efficiency. Placing it after the cluster breaks the causal chain, as the first cluster of the first image is never predicted. The class token trick, a hidden advantage. One of the most subtle but powerful changes in STAR is repositioning the class token. In traditional Vision Mamba models like Vim or vMamba, the class token is placed in the middle of the sequence. But in STAR's long sequence setup, the model processes information in a left-to-right AutoRegressive way, and by the time it reaches the end of the sequence, it has seen the full image. So why not put the class token at the end? The authors do exactly that. And the result? A 0.3% improvement in EMA accuracy, a significant gain in a field where every fraction of a percent matters. This small change aligns the model's architecture with its training objective. The final state of the sequence should contain the full image representation. Results that speak for themselves. After 300 epochs of autoregressive pretraining, the STARB model achieves 82.9% top 1 accuracy on ImageNet 1K after end-to-end fine-tuning, outperforming not only contrastive learning and MAE, but even ARM, which is the previous state-of-the-art for Mamba-based pretraining. But here's the real kicker: STAR is faster. 6.6x faster than MoCo v3, 1.4x faster than MAE, and 8x longer input sequences than ARM. And when trained for 1,600 epochs, STARB hits 83.5% accuracy, nearly on par with vMamba, a much more complex model. Even more impressively, STARB matches RegNet Y16G, a high-performance CNN, while using only 85 million parameters and 1,301 images per second throughput. This proves that lightweight models can compete with heavy ones, if trained with the right pretraining strategy. Why this matters for the future? STAR isn't just a better pretraining method, it's a new paradigm. It shows that long-sequence autoregressive pretraining is not only feasible for Vision Mamba, but essential to unlock its full potential. It demonstrates that simple architectural changes, like adding a separator and repositioning the class token, can yield massive gains. And it opens the door to new research directions. Can we use STAR to pretrain on video sequences? Can we extend it to multimodal tasks? Can we apply similar ideas to other long-context models? Final thoughts. STAR proves that sometimes, the most powerful innovations are the simplest. By adding a single, carefully designed separator, the authors transformed Vision Mamba from a short sequence model into a true long-context learner. This work isn't just about improving accuracy, it's about rethinking how we train vision models. It challenges the assumption that pretraining must be image by image. Instead, it shows that context across images is valuable, and that Mamba's strength in long sequences should be fully leveraged. So if you're working on lightweight vision models, sequence modeling, or self-supervised learning, STAR is a must-read. It's not just a paper, it's a new direction. And for the future of vision AI, the sequence has only just begun.